So I'm Kris Gorissen, but same company. We are neighbors in the company, so also the same story. We've got a request to do a presentation on maximalization of efficiency and sustainability in breweries. So we had some ideas or some topics in mind. We could have said something on biogas valorization. We could have said something on reduction of water losses in water treatment plant, process water treatment plants. But we've chosen, because we only have 20 minutes, to discuss one topic, and that's how to reduce brewery water footprint. In brief, we will speak about, first of all, the brewery water usage, because that's what we want to reduce, the water footprint. First of all, what's important, and that was also mentioned by in the previous presentation, is the brewery housekeeping, how much water is used in brewing, packaging processes. So that's something to be optimized. That's a first step in this process of reducing the water footprint. The second step is more or less an end-of-pipe solution, and that's what we call a boomerang water technology, where we will upgrade, filtrate, purify bioeffluent from the biological wastewater treatment plant of a brewery towards process water or potable water. We will also touch the drivers and points of attention for this technology. And then to finalize, I will present a brief brewery case study with a water mass balance and also something on the financial figures of such project. But I will start with a very brief introduction of the company Waterleau. If I'm not mistaken, most presentations are fairly scientific. We in Waterloo, we also do science and technology, but we do it on a full scale. We do full-scale projects, so it's, let's say, a little bit more applied science than what is presented in the other presentations in this conference. Waterloo, to be very short, is a company doing environmental technologies, environmental projects in the fields of water, air, fire, which is new energy, renewable energy, earth, which is waste and biosolids. We have over 50 technologies, almost 30 patents in these different fields, and we do projects more or less all over the world. So now the real topic of today, how to reduce the brewery water footprint. A typical brewery, or let's say Western brewery, has somewhere between, let's say, 4 and 6 hectoliter per hectoliter water consumption. And most breweries nowadays will be around 4.5, 4 hectoliter a hectoliter. If you go to, let's say, other continents, if you go to Africa, for instance, there are examples of breweries that are using double the water, so between 10 and 15 hectoliter a hectoliter, so they have more work to do. A first step is, okay, let's have a look at brewery housekeeping. Where are we consuming the water? How can we minimize that? How can we optimize that? I'm thinking of monitoring of water consumption, water-efficient CIP, water-efficient packaging, membrane filtration instead of kieselguur filtration, save some water. Process chemical use can be optimized. You can do some things in the process water treatment plant to minimize water losses. That's a step most breweries in the Western world have taken, and they end up at 4, 4.5 hectoliter a hectoliter. If you want to take the next step, because you will always need water to do sip cleanings, you will need water to brew your beer, you will need water to chain lubricate, what's also one of the topics in the previous presentation. You will always need a certain amount of water. To bring that down to, for instance, 3 hectoliter a hectoliter, we need to implement an end-of-pipe technology. And that's, let's say, where our technology kicks in, the boomerang technology. It's bioeffluent recovery by means of membrane filtration, 2-step membrane filtration, ultrafiltration, reverse osmosis, and like this we can purify or upgrade the bioeffluent, which is coming out of the biological wastewater treatment plant, to potable water, process water. You have some different, let's say, ways of doing that. If you have already a biological wastewater treatment plant, then you could, and that's what in most cases happens, then you could, then you could do a ultrafiltration followed by a reverse osmosis. That's what you also see here in this 3D. So here a skid with ultrafiltration membranes followed by a skid with reverse osmosis membranes. If you don't have a biological wastewater treatment plant, then you could combine the ultrafiltration part with the biological treatment part by means of an MBR, a membrane bioreactor. But okay, we won't go into too much detail in that because time is too short. The definition of boomerang water for us is that it's bioeffluent recovery, means that you need to have a biological treatment, and you need to have a certain quality of water to start with. And you need the biological treatment. There is no way that you can send the raw wastewater directly onto these membrane installations, because then you will have biofilms fouling and you won't have a stable operation. So you need to have the wastewater treatment plant in place. Then boomerang water for us, it's also membrane technology. You could think of some other technologies. If you really want to go to this high quality waters, then you need to do ultrafiltration, reverse osmosis. And then you produce potable water or processed water. So in general, after the reverse osmosis, the water quality is even better than the water quality coming out of the tap. Better in the way that there is less salts inside, less dissolved components in this water. So 3 conditions must be fulfilled to have a successful boomerang project or bioeffluent recovery project. First of all, the bioeffluent must be of acceptable quality. Means that organic parameters, typically BOD, COD, should be low enough to avoid problems with biofouling on the membrane skids. A second one, and that's for me personally, or technologically, the most important one. What you do, you have 100% or 100 cubic meter bioeffluent, and actually what you do in these membrane filtration processes, you make roughly 70 cubic meter or 70% ultra pure water, processed water, and all the components which are dissolved in the water are concentrated in the other 30%. So you need to find a way out for this RO concentrate. So the RO concentrate stream must be disposable. So that's a very important point, because sometimes legislation does not allow for it. Depends from country to country, from case to case, but that's an important one. We will touch that a little bit more in detail in another slide. And then, of course, you have also the third point, where the production must allow for reuse. So technically, there is no problem at all to upgrade bioeffluent to potable water. And that's what they also do in Las Vegas. That's what they also do in Singapore. And very water scarce areas, they are forced to implement the technologies. So technically, technologically, there's not really a problem. Financially, of course, you need to do an investment. You have operational costs, so you need to have a business plan around that. And then in a brewery, certainly, it's also important, the psychological barrier. And most breweries are, let's say, not too fond on, let's say, brewing beer from wastewater, because that's marketing-wise a very difficult point. Something on the membrane filtration technology. So here you see what we call a membrane filtration spectrum. So first we start with the ultrafiltration here, which is, let's say, a very fine sieve where all particles, colloidal material, turbidity, microorganisms are sieved, are taken out of the bioeffluent stream. Then in a second step, the reverse osmosis step, the XL reverse osmosis step, there we are going to remove the components which are dissolved in the water. We think of salts, we think of some organic substances, color, also viruses. Part of the viruses will pass the ultrafiltration, so they will all be retained on the reverse osmosis membrane. So that's let's say, the final polishing step, which you need to have this high-quality water. So you can ask, okay, why do we need this first step, this ultrafiltration, if we actually need the reverse osmosis step? Because the ultrafiltration step protects your reverse osmosis membrane from clogging. If you would send all these colloidal material, suspended solids to the reverse osmosis membrane, you will have a lot of operational problems, a lot of sip cleaning, fluxes which will go down. So that's not working. So you need to have the two-step approach. How does it look? For this one is an example which we've built in a potato factory in Belgium. It's a 50 cubic meter plant. So let's say 2 trucks of water an hour, which are saved or which are recovered. And it takes a footprint of more or less 200 square meters, so 20 on 10 meters. So it's also a quite compact technology. This is how it looks in real life with the ultrafiltration membrane skid over here. And then the second step, the reverse osmosis skid over here. Something on the drivers for bioeffluent recovery. First of all, and that's always like that, you have financial drivers. Companies that are implementing this technology, they are facing increasing city water costs. They are facing wastewater discharge costs, which also go up almost every year. In some countries more than in others, so that's why we need to study case by case. A second important driver is water availability driver. So if you have your factory, your brewery, in a very water scarce area, I'm thinking of certain parts in Africa, I'm thinking of also certain parts in Latin America. There could be very important to reuse part of the water you generate, wastewater you generate yourself, because then you will get less dependent from external water providers. Sometimes you also have a limited groundwater permit. If the limit is reached, then you need to think of something else to increase or further increase the production. And that's when these technologies come into sight. Water quality is also a driver. So the water quality coming out of this boomerang system is very high. In some breweries, they take in city water quality, which is not good enough, and which would need treatment anyhow. Then it might be interesting to use the bioeffluent, which you have available yourself, as a water source instead. And then what's also more and more important, certainly for multinationals, is what we call the corporate social responsibility. All companies want to decrease their water footprint, not only the costs, but also the water footprint. And some even want to go to a zero discharge factory or brewery. And of course, in most of these projects, it's a combination of these drivers, which is a real driving force for the project. On the other side of the spectrum, you have the drivers, but you also have the points of attention. So what needs to be fulfilled, what needs to be tackled before we can implement such project. That's first of all, like I've mentioned before, the bioeffluent quality. So you need to have a biological wastewater treatment plant. If you don't have it, you need to invest in a biological wastewater treatment plant and a boomerang plant. Most Western breweries have the biological treatment plant already. Then the second one, and in my opinion the most important one, what to do with the RO concentrate. You could, in some cases, you are allowed to do direct sewer discharge. In Germany, for instance, I know that in some, maybe not in all regions, but in some regions, I've worked on projects where they pay for every cubic meter they discharge in the sewer network. No matter what, there are limits, but the limits are not that strict for what you discharge in the sewer network. So there, the RO concentrate, which is still relatively clean water, could be discharged into the sewer. So that could be a solution. That's not everywhere possible. If it's not possible and you need to discharge, for instance, under a COD limit, an organic content limit of 100 ppm, then a solution could be that only part of the bioeffluent is reused, and that we blend the RO concentrate with the other part of the bioeffluent, which is not reused. And like this, let's say the contamination is diluted, and we can stay within the discharge limits. Another possibility, but that's quite expensive in operational and also in investment cost, is to do an RO concentrate polishing treatment. Could be biological polishing, could be advanced oxidation processes, could also be evaporation. You can all feel already that evaporation is a very energy-consuming process. But in some cases, there are cases in India, in Mexico also, where costs for 1 cubic meter of city water go up to $5, $6, $7 or euros a cubic meter, and then this can be financially, or you can build a financially solid business case even with these evaporation processes. If you do evaporation, you can close the loop completely. You can go to let's say, a zero discharge brewery, and you can recover, let's say, 99.5% of all the water which normally is discharged. In Belgium, in Flanders, and then also in many other countries, it's always the discussion. What you do, actually, you have the bioeffluent. You have a certain amount of contamination which is still present, which is fairly low, but it's still present. What you do in this boomerang technology is concentrating the amount of organics, but the load is remaining the same. And on the one hand, the authorities want the companies to, let's say, to decrease their water footprint, to save on the water they take in. But on the other hand, they say, okay, sorry, we have legislation, you need to obey to a certain concentration for discharge, which is very often the bottleneck for a project like this. So that's, for these projects, a discussion which needs to be done with the authorities, and up to now it's very often a very difficult discussion, because there is a legislation in place, but it's not fit to allow the breweries to decrease their water footprint. So then, let's say a typical saying then is dilution a solution for pollution? Because in the end, you're discharging the same COD, same nitrogen, same phosphorus to a surface water, to a sewer, but only a little bit more concentrated. That's also something that needs to be tackled up to now, case by case, because the legislation in most countries is not that far yet. What's also important is you need to have a certain economy of scale to make a project like this feasible. You have legal permit requirements. Is there a wastewater treatment plant available? If you have it already, the capex investment will be lower. What water quality do you have? What water quality do you need? That's also important to take along in the project. Savings are also not only made by the water intake, but also by the reduced discharge. And all the water you reuse, you are not discharging to the sewer, to the surface water, so you're also not taxed for that. So that's also in the business model is also playing a role. The final point of attention is the psychological barrier, and that's last but not least. That's certainly in brewery industry, because we have quite some references in food industry already of these projects, but in brewery industry, this psychological barrier certainly is there. And what I'm showing here is something which was, I think, 2 weeks ago in the newspaper, that your colleagues from the University of Ghent, they've brewed beer starting from upgraded, purified wastewater from a brewery. So it's technologically, that's perfectly possible and perfectly safe. Now something on a case study for the brewery water mass balance. So say we will look at a brewery with a capacity of 6 million hectoliter. That's more or less the size of the InBev or Stella Artois brewery in Leuven. So it's quite big size. Say it has a current water ratio of 4.5 hectoliter a hectoliter. And from this 4.5 hectoliter a hectoliter, 1.5 hectoliter a hectoliter is going to the beer itself, to the product, and to losses, evaporation losses. So from the 10,000 cubic meter a day water consumption, you have 3,300, 1/3, which is going, let's say, to the product and to some losses. So it means that all the remaining water, the 6,666 cubic meter a day, will be wastewater in the end of the day. Schematically, it looks like this. That's a traditional scheme for a brewery. So you have the brewery, which is 4.5 hectoliter a hectoliter. So the housekeeping, the packaging, they do it fairly efficient already. They take in 10,000 cubic meter a day of new water, city water, borehole water. 1.5 hectoliter a hectoliter, or 3,300 cubic meter a day, is going to the product and losses. All the rest is going to the wastewater treatment plant, is treated, and is discharged to a surface water or to the sewer. If we implement a boomerang technology, then this will all remain the same, but this 6,600 cubic meter a day, we recover 70%, which is 4,600 cubic meter a day, or 2.1 hectoliter a hectoliter. We recover it back to the brewery. Means that we don't need 4.5 hectoliter a hectoliter, but more or less half of that, 2.4 hectoliter a hectoliter. So the new water can be reduced drastically to 5,300 cubic meters a day. The beer production and losses, they remain identical, of course. And the discharge comes down drastically to less than 2,000 cubic meter a day, or 0.9 hectoliter a hectoliter. Summarized, up to 50% water saving, more than 70% reduction in the discharge. And the psychological barrier should not be a psychological barrier. Why not? Because there is no bioeffluent that should be reused for brewing the beer. It could be reused for packaging, it could be reused for CIP cleanings, for cooling, as cooling water, but we should not reuse it for brewing beer. For that, we can still use the new water. So here we use, or we have 1.5 hectoliter a hectoliter, and still we need to bring in 2.4 hectoliter a hectoliter. So the psychological barrier should actually not be a psychological barrier, because you can keep that completely separate. The boomerang water will not be used as brewing water, and the new water, of course, can be used as brewing water, because 2.4 hectoliter a hectoliter still is much bigger than 1 hectoliter a hectoliter. This size of project, what does it mean in Belgium, in Flanders, let's say, financially? What's the return on investment? Very briefly, this size of project, we will reuse almost 200 cubic meter an hour of bioeffluent. 195 cubic meters an hour of processed water is produced. Means 1.5 million cubic meters per year, with 70% overall recovery. The investment for such project is roughly 1.8 million euro. And then, of course, you have operational costs: electricity, chemicals, membrane replacement, maintenance, and also operator hours. If we put everything together, you have the benefits on the one side of the balance, where you save on the city water intake. If we calculate with slightly more than €1 a cubic meter, that's 1.6 million euros a year. In Flanders, you can also save a little bit, but not a lot on the discharge tax, because you're taxed mainly on the loads and not on the quantity of water. Where in Germany, in lots of areas, you're taxed on the quantity of water. So there you can save then 70% on your discharge tax. Now I've taken as an example a Flemish case where you save 50,000 euros. So altogether, you save 1.7 million euros a year. And then, of course, You have your operational costs, electricity, chemicals, membrane replacement, maintenance, operator hours, let's say more or less 800,000 euros a year. So it means you have an operational benefit of more or less 900,000 euros. Given that the capex investment is 1.8 million euros, you have a return of investment, or depends on how you calculate it, but more or less 2 years. You have an ERR rate, which is, let's say, a financial. If you would put the same money in the bank should give you 25% interest. So, means that it's even financially a very interesting project. It's paid off in 2-3 years' time, and the water treatment plant lifetime is more than 20 years. So certainly on the long run, it's an interesting project. This, of course, is for a big brewery. So here you have the rules of thumb. We can say that a project could be feasible if you have more than 25 cubic meters an hour of wastewater. If you have between 1 and 2 euro per cubic meter of total cost savers. If you can use borehole water, which you can have more or less for free, it will be difficult to have a positive business case. If you need to bring in city water, of course, that's a game changer. If your brewery wants to expand and you're taking borehole water, but the amount of borehole water is limited, that's also a game changer, because then it's not a project on its own, but doing the project also means that you can brew more beer, that you can sell more beer. So that's also something to take into account. This is, let's say, the presentation on the boomerang water, on the bioeffluent recovery. If you have any questions, shoot.
Have you made the same analysis for melting plants?
For melting plants, it's also, the technology remains the same. Let's say the contamination of the wastewater, it's not exactly the same, but it's very similar. You also need a biological wastewater treatment plant, and you could also reuse the water using the same technologies. Okay. Absolutely. We are even, in Belgium, there is even a maltery which is thinking in that direction, but they're not there yet, but quite some work done there already.
Thank you.